Okay, so in the previous graph theory video, we saw the notion of a rooted tree and some other related things. Today we are going to continue our discussion with this new thing, the normality of a rooted tree in a graph in which the tree is a subgraph. And it starts like this. A rooted tree T that is contained in a graph G is called normal in G if the ends of every T path in G are comparable in the tree order in T. If T spans G, this amounts to requiring that two vertices in T must be comparable. If they are adjacent in G. Okay, we will make sense of what these things mean. Now, this is followed by an example. So let's just draw the graph in that example first, and then we will see what these things mean. So in this example, the graph has 18 vertices. Let us draw it carefully. There is a possibility of making mistakes here, specifically the possibility of missing a vertex, because we have 18 vertices in this example, but they are not labeled. And I have in fact remarked previously also about using a ruler to draw the edges. It looks good, but in this case it is necessary. You will see why. Although one can in fact draw an edge in a graph in any manner one wants, just you have to link to adjacent vertices with something, with an edge. It does not matter how you draw the edge, but in this case straight line edges will give us an advantage. So let us first draw the graph. then we have two vertices here and they are linked like this. And then more vertices on this side. Let us see if we have got 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yes. So this is a tree T, and it's a rooted tree where this vertex is being regarded as the root. But the actual graph G, in which T is a subgraph, has other things also. Now T here spans G. That means in G there are no extra vertices. This is all we have. Okay, these are the only vertices. So T is going to be a spanning tree in G, but extra edges are there. Now those edges have to be drawn carefully, which are there in the graph but which are not parts of the tree. So this is one edge. These two vertices are adjacent in G. This is another edge. Let us first see the edges that are incident on the root. There is an edge like this, and then there is one edge like this, and there is one edge like this also. Okay, so what is the degree of R here? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yes. So we are done with R and we are done with this other vertices also. Now we come to this one. Okay, so first of all, this is, the entire thing is somewhat confusing. These two are adjacent. Oh, I have drawn it in this. It does not matter. And this is also adjacent to this. What else? Okay, so just like this edge, there is another like this. And then this one is also adjacent to this. One more. These two are, where am I going? Yeah, here. Okay. So these are, this side is okay. Now these two are also adjacent. What else? Making this one adjacent with these two higher vertices. Okay, so let us now check its degree. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yes. What about the degree of this? From here, 1, 2, 3, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yes. This one has degree 3. And what about this? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So this is our graph, and it is showing a normal spanning tree with root r. Now let us see what the definition is saying. A rooted tree T like this one is that is contained in a graph G, that is a subgraph of G, is called normal in G if the ends of every T path in G are comparable in the tree order in T. So there are two things there for us to recall. One is a T path and one is this tree order. Okay, now most of the things in graph, the terminology, graph theoretic terminologies, are very intuitive, so much so that just by looking at something, for example, tree order or say a tree itself, that alone gives you an idea of what the thing is. But sometimes that is not the case, and this T path unfortunately is one such slightly confusing term. I also got confused because I forgot what a T path means while going through these things. So the confusion may arise like this. You may think that a T path is a path in T, in the tree T, but that is not the case. You see, we have already seen some equivalent conditions for a graph to be a tree, that fundamental theorem on tree, you can call that, in which T is a tree if and only if T is maximally acyclic. Those things we have already seen. Now in that we have seen that in a tree any two vertices are joined by a unique path. There is a unique path linking any two vertices in a tree. One may confuse that with a T path. So let us now recall a situation that we saw when we came across paths and cycles. Say you have a graph G in which you have a subgraph H, and in H there are two vertices, say U and V, and there is a path in G that links U and V, but the condition is that that path has only its ends U and V in H. Nothing else of the path is in H. No inner vertices of the path is, no inner vertex is in H, and also the edges are also not in H. Such a path is called an H path in G. An H path is a path that starts somewhere in H, leaves H completely immediately, and then again comes back somewhere in H. So such a path is called an H path. So that's why a T path is not a path in T, but a path that leaves and comes back to T. Okay. So what we are saying here is that the tree T in a graph G is called normal in G if the ends of every T path in G are comparable in the tree order in T. So let us recall that thing also. Now tree order. We have seen that if we have a tree and in which say we choose a vertex to be root, then we can use this entire thing to partially order the set of vertices in this tree, and that order just goes like this. Say you have two vertices u and v. Now we know that there is a unique path. You look at this example itself. There is a unique path joining the root and v, and that path contains u. Okay, when that happens, we say that u is less than or equal to v, and we say u is in this case u is strictly less than v because u and v are different, and this turns out to be a partial order. Partial order in general not a total order, because vertices may be there that are not comparable. For example, if you look at this vertex w, v and w are not comparable. The unique path linking v and r does not contain w. The unique path linking w and r does not contain v. So neither is v less than or equal to w, nor is w less than or equal to v. So they are not comparable. So in general you can say that this is a partial order. It will be a total order, of course, if the tree is just a path and you choose one end as the root. So now with all these things we are saying that you have a graph G. In that graph you have a subgraph, that is a tree T, that is a rooted tree, and every T path in G has its ends that are comparable in that tree order. Okay, if that happens, then we say that T is normal in G. Now let's look at this example. You see, I was saying that there is an advantage to using straight line segments to draw the edges in the tree. That is because now we can see which edges belong to the tree and which edges are outside the tree. So let us consider a T path. Because the ends of a T path must belong to T, you can now consider T here. Say. So this is your T. I need ink. Give me a moment. So this is our T now. We now have to consider a T path which has only its ends in T. Now in this case, since the tree is a spanning tree, so we don't have any vertex in G that is not in T. So any two vertices you choose will be in T itself. For example, you take this vertex and say this vertex. So according to our definition of a T path, we can already see that there is a path in the tree T between these two vertices, but that is not a T path. This edge forms a T path along with, of course, the ends. So this vertex followed by this edge and this vertex, that is a T path, and its ends, say we call this X, this is X and this is Y. Its ends are comparable. The unique path from Y to R is this in the tree that contains X. So Y is greater than or equal to, in fact Y is strictly greater than X. Anyway, the thing is that they are comparable. Now you can see one thing here, that because the tree we are choosing, we have taken here is a spanning tree, so every t path will have only one edge, because there can be no inner vertex. No, those inner vertices by the definition of a t path cannot belong to t, but everything here is in t. T is all we have, I mean at least in terms of vertices. So any t path we consider is going to be an edge that is not in t. So we can see many t paths here, say joining this one and this one. In fact all the edges you see here that are not parts of t, all of them form a t path along with their ends. And you can see that any two such ends are actually comparable. Okay, now how can things go wrong? What sort of edge will make t not normal? If you had an edge like this, we don't have that in G, but suppose you had an edge like this, then for that modified G, t will not be normal in that G. Why? Because these two vertices, this is Z or Z, these two vertices are not comparable in the tree order that we have in T with respect to this root. The unique path joining Y and R in the tree does not contain Z, and the unique path joining Z and R does not contain Y, so they are not comparable. Okay, so non-comparable points should not be, I mean there should not be any link between them, because if you find such a link, then I mean in this case that link of course will have only one edge, but in general it may be a path that is not necessarily an edge, specifically when T is not a spanning tree. So if such a linkage is found in G, and if this G is something bigger, say a bigger graph in which T is not a spanning tree, say we had extra vertices like this, and you found a link like this, then that link would give you a T path, because that would be a T path. However, its ends are not comparable. Okay, so that can create a problem. In this graph, we don't see such things. Okay, so such links are not present here. Had they been present, they would have been some such single edges. That's what the next line says. If T spans G, as we have in this case, this amounts to requiring that two vertices in T must be comparable if they are adjacent in G. If they are adjacent in G, this with using these extra edges, then they must be comparable. Now still this entire thing looks somewhat difficult to grasp. So let us now see what is actually going on inside this whole thing. We have seen how we drew this graph. We first drew the tree and then we supplied the extra things, which in this case are just edges. In general, that may involve putting extra vertices and then extra edges. So you may have noticed one thing. Now we are going to be a little vague because we just need the idea. Say you think of the tree as a tree that is growing from the root. Okay, so the branches come out, many different branches come out. So this is the skeleton of the graph, this graph. Okay, you don't consider this as like this graph only. I'm just saying in general there is a root from which the tree is growing. Okay, the tree has grown and the skeleton is ready. Now next what we do, if we have extra vertices, okay, or okay, let's just leave that thing. Let's see this case itself. Now the tree has extra things apart from these branches. It has leaves. I'm just simply considering the analogy with an actual biological tree. Okay, there are extra things. So those extra things look like this skeleton. It's like someone has expanded the skeleton in some way by, say, putting extra edges like this. And that is the whole graph. Looking at this graph, you can see that the graph is somewhat like the tree itself, only an expanded version. It's like we are an expanded version of our skeleton that we have underneath all the skin, flesh and everything. They have expanded and they have formed the person, or here it has formed the graph. Okay, now that is because the tree is, I mean, we are drawing the entire thing in such a way that the tree becomes a normal tree in the graph. The graph somehow is looking just like the tree, only with some extra things. Now if you want to create problem, if you want to make the tree not normal in a graph which you draw by putting something extra, say one extra edge like this. Now this extra edge does not reflect the growth of the tree, how the branches have grown, and we have just sort of expanded those branches in a way that is not reflected by this extra edge or extra link. It's like everything has grown and done, then suddenly some thing from outside has attacked the tree, some parasitic plant or something like that. That is not a part of the tree, the biological tree. So that is extra, and now the entire structure is such that the tree is not normal in this new structure. So those extra links do not reflect how the tree has grown. So if you have those extra links, the tree is not normal. Otherwise it is normal. So they are saying if T spans G, this amounts to requiring that two vertices in T be comparable if they are adjacent in G. So the vague way of saying that the entire graph somehow follows the growth of the tree, that is made precise by this order relation, comparability. Okay, that the growth has gone from a lower stage to an upper stage, like that. Okay, so that is the notion of normality. Now if you want, if you want a concrete example of I don't think there is any need to consider another graph. You can make this tree not normal in a graph by, again, that you put some extra edge like this between non-comparable vertices in the tree order. Or if you want to complicate matters further, you can take extra vertices and you can create a T path, the ends of which are not comparable. So then this tree will not be normal in G. Okay. Now this fact that a graph grows like a normal tree in it can be used to gain insights about the graph itself. So we are now going to see a result. I made the mistake of interpreting a t path as just a path in t, and then the confusion reigned. But then I understood that I was wrong and I rectified myself. So the author writes, a normal tree T in G can be a powerful tool for examining the structure of G because G reflects the separation properties of T. So the next thing is this lemma one 5. Oh, so we have already seen things previously. Oh, what the hell am I thinking? This is not a new section, no? We have been going through trees. Okay. Let T be a normal tree in G. There are two parts. Part 1, any two vertices x and y in T are separated by this set, is separated in G, of course, by this set. We will have to recall what this thing is. This is the down closure of x. We saw these things after seeing the notion of a rooted tree. If, and in the second part, if S is a subset of the vertex set of T, which in this case is also equal to the vertex set of G. That means in this second part, T is a spanning tree in G, and S is down closed. Then the components of G minus S are spanned by the sets. The components are okay, they will be up closed, that hasn't been said here. Anyway, so G minus S are spanned by the sets this with X minimal in T minus S. Oh, and now I noticing something. It should also be mentioned. If you have a tree, a rooted tree, and say that is your G, there is nothing else in G. The tree is a spanning tree and that itself is your graph. Is the tree normal in itself? You have the tree, whatever it is, like this, and say this is their root. Is the tree normal in itself? It is, because if you consider any two vertices, okay, do they form a T-path? They don't form a T-path because the vertices are themselves vertices in T, and there is already a unique path in T joining them, linking them, and there is no other edge outside of those that we have in T. So there is no T path between two distinct vertices. So the statement that the ends of a T path are comparable in the tree order in this case is vacuously true. And there is one more thing also. Nothing is saying, this is also important to notice, nothing in this definition of normality says that the ends of a T path, oh, but then it will not be a path. No, I mean, we cannot have something like this. I mean, it starts here and ends here itself. No, then it will not be a path, it will be a cycle. Okay, so that case does not arise. Anyway, so a rooted tree is normal in itself. Okay, so we have realized that. So let us now see the proof. So the proof goes like this. So this is 1, there are 2 vertices and they are separated in G by this set. So let us now recall first what these sets are. This set is called the down closure of the vertex X and is the set of those vertices in T. In T, of course, because okay. No, this need not be only in T. In G, such that y is less than or equal to, let me just see, okay, what I am saying is correct or not. Should we have T here or G here? If there is nothing wrong if we write G here, but the thing is that if our tree is like this and in the graph G we have a vertex that is not a part of the tree at all, this vertex lies outside the vertex set of the tree, then it does not make sense to ask whether this vertex is less than or equal to this, say you have X here, because the partial order relation is only on the set of vertices in T. We can say that those y belonging to G such that this, but then ultimately we are talking about the vertices in T. Anyway, so the thing here is that this is the set of those vertices that are less than or equal to X in the tree order. Or if you really draw the tree like that, so that the root is the bottom vertex and then you have those levels, okay, according to the heights of the vertices, then this thing is the set of all those vertices that lie below x, and in fact it will consist of those vertices. If you think of it carefully, it will consist of those vertices that lie on the path joining x and the root. Okay, so that's the thing. That's what this set x is. So it is the down closure of x. So what we are saying here is that two vertices x and y are separated in G by the intersection of the down closures of x and y. And separated means what we already know. You think of any xy path, that is a path in G whose ends are x and y. That path will intersect this set somewhere, and since this is a set of vertices, that path will have at least one vertex that is in the down closure of x as well as in the down closure of y. That's what we are going to consider. So let us start by taking any such path. Let P be any xy path in G. Since T is normal, the vertices of P in T form a sequence like this, which starts with x. We can call that T1, and there are possibly other things in between, and it ends at y, which is the Tn, such that Ti and Ti plus 1 are comparable. For all i's that makes sense. I mean, the highest value of I in this context you can take is n minus 1, so that Ti plus 1 becomes Tn. You cannot go higher than that. Are always comparable for all I in the tree order in T. What has the author said here? We have to understand that first. So this is our tree. Say this is the tree T. In this part 1, we are not saying that the tree is a spanning tree. So there may be other things outside the tree in G. So G is there in the background, possibly bigger. But the vertices x and y are in T. Now note that we have considered any xy path in G, okay, not in T. Any path in G joining x and y, and this is not a T path, this is any path. So it can go in any manner it wants. It can enter T and leave T any number of time it wants, but ultimately it has to come back to y. That is the most general situation. No one knows what is happening in between, but it may come back to T, it may leave T, it can do whatever it wants. Okay. Now what we are saying is that you can understand the situation. No? Here it has left t, and then here at this vertex it has again come back to t, and it continues several times, possibly like this. Or it in fact may turn out to be itself a t path also. That can also happen. So now what the author is saying is that since t is normal, the vertices of P, this is our path P, in T, not outside T, form a sequence like this such that the adjacent terms in this sequence are comparable for all possible i's in the tree order. So there are two types of vertices of the path P in T. These vertices, these adjacent vertices whose edges, the edge that joins them, they are parts of T. Okay. And those vertices such that the links between them are not parts of T. You see, although I have drawn it as if this edge, say the next one, this is T1, there will be a next one, T2. It seems like the edge T1, T2 is part of T. It may not be. We have already seen in that example, it may actually be outside T also, because the path P we are choosing can be any path. You can say that, okay, then if we don't consider that outside edge, how are these two vertices linked? Because the tree T by definition is a connected graph, so these two must be the ends of some path in T. Yes, there may be some other path in T joining them, but that path we haven't considered to be a part of P. We have considered P like this, say. That can also happen. Okay. Now, if the vertex, if the edge that joins two such vertices, the Ti and Ti plus 1, this is Ti and this is Ti plus 1 in general, if that edge belongs to T, then Ti and Ti plus 1 are comparable, and this is a fact which has already been mentioned when we introduced the tree order. Do you know why? Because you see, if you have a rooted tree with R, some root, and say you have two adjacent vertices, okay, but the edge is actually an edge in the tree. Now there will be a unique path joining R and Ti. There will also be a unique path joining R and Ti plus 1, but we are considering that one first. Now there are two possibilities. That unique path may not contain Ti plus, may not contain this edge, or it may contain that edge. If it does not contain this edge, then we already have got a path joining Ti plus 1 and R, which is obtained by introducing this extra edge to the existing path. And you can see that now by the definition of the tree order, in this case, Ti plus 1 will be greater than Ti. But if this is not the case, if this edge turns out to be an edge joining Ti and R, that is, it becomes a part of that unique path joining Ti and R. In that case, Ti plus 1 will be less than Ti. Whatever the case is, in any rooted tree, with respect to the tree order, the ends of any edge are comparable. Okay, so any ti and ti plus 1 that have been joined by an edge between them which is a part of the tree are comparable. And if you obtain something outside, say you consider an edge that is not in T, if that happens to be a part of P, then that edge, like that example, along with its ends is a T path. So by the definition of normality, its ends should be comparable. Now note that we are only considering edges. Why? That is because we are considering paths like this, and the situation is such that these vertices are in T. The edges joining them may or may not be in T, but the vertices are in T. Okay, so that's why there is a single edge between two consecutive T's, Ti and Ti plus 1. But when you come to these points of exit and entry from T and into T, so this is your some Tj and the next one is Tj plus 1, which in the actual path P are quite far away, but in this sequence they are consecutive, of course. Now for them this is a T path whose ends are this Tj and Tj plus 1 again. So by the definition of normality, they are also, those exit point and entry points are also comparable. So that's why Ti is always comparable to Ti plus 1 or any I in the tree order in T. Okay, so we have understood the meaning of this line. Here the proofs go in a fashion which is so unlike what we see in other parts of mathematics. But that may be because I am new to graph theory. I don't know much graph theory. I saw these things way back, and probably I never saw this much graph theory. So that's why my interpretation and the techniques that I am using to understand these things, they may be naive and somewhat foolish, but we have to do what we can do. Maybe after learning graph theory quite a bit, we may develop some intuition and some techniques that we already know in other parts of maths. Okay, so that's the situation here. Now consider a minimal subsequence of vertices. Consider a minimal such sequence of vertices in P intersection T. Now this line may be slightly confusing. Minimal with respect to what? Minimal with respect to number of vertices. Now you may get confused in thinking, okay, in P intersection T we have what we have, so what minimal? I mean, how do we change things? The change is not in the set P intersection T itself, because although P is any path joining x and y, once chosen P is fixed. So P is there and we can't change that. T is also fixed. So this P intersection T, all these vertices, then these vertices, these ones, all the vertices that lie in T and also in P, they are fixed. Okay. But minimal with respect to this property, not just vertex number, but also with respect to this property, that is ti and ti plus 1 are comparable for all I in the tree order in T. Because you see, you still may be somewhat confused. We have shown that the consecutive TIs are comparable, so what? So how are we minimizing things? That is because consecutive T's are comparable, but if you don't consider some T's in between, and if the resulting less number of T's also turn out to be comparable, I mean the consecutive ones, that way minimizing. Okay, so consider a minimal such sequence of vertices in P intersection T. So that means now possibly we are not regarding some T's in between, or here in P intersection T somewhere, and that gives us a minimal possible such set in which Ti and Ti plus 1 are comparable. If you remove anything from that minimal, this property will not be there anymore. Okay, it will be broken, it will be gone. In this sequence, in such a minimal sequence, we cannot have a situation like this. Ti minus 1 is less than Ti and Ti is greater than Ti plus 1. Why? Let me show you why. You see, say you have such a situation. Ti minus 1 is less than Ti and Ti is greater than Ti plus 1. Ti minus 1 being less than Ti, what does this mean actually? It means that the unique path in the tree that joins the root R and Ti contains Ti minus 1. Okay, Ti minus 1 is a vertex in that path. Similarly, we will have this also, and to show that Ti minus 1 is less than Ti, we have drawn the thing vertices in this manner. Ti minus 1 and Ti plus 1 are both at lower levels than Ti with respect to R, but this is a single vertex, no? So that's why okay, so these two coincide. Now the situation is like this. Instead of joining it here itself, we have kept it somewhat general and say the paths have converged and met here, and then they have progressed together, or they have come down together to R. But we are in a tree, okay, and these paths are in tree, so we cannot have this cycle. It should be a single path, and that single path definitely will contain both Ti minus 1 and Ti plus 1, and that would make them comparable. Because if see, in that situation, Ti minus 1 and Ti plus 1 belong to the same path linking Ti and R, and that path also belongs to our tree. If Ti minus 1 happens to be above Ti plus 1, then it is greater than Ti plus 1. Otherwise, it is less than Ti plus 1, but they are comparable. So that's the point here. But then what happens? Fine, they are comparable, so what? And in that case we can get rid of Ti, that's the thing, and still keep that property intact where consecutive vertices in the sequence are comparable, and that in turn would contradict minimality of that sequence. So the next line says this for any I, since Ti minus 1 and Ti plus 1 would then be comparable. And deleting Ti would yield a smaller subsequence, which is not possible given the minimality of this sequence. And that is why we will come across a T, some Tk, which is satisfying these inequalities in that ordered relation, and also at the same time satisfies another sequence of inequalities where there is one smallest element in that sequence with respect to that order. That's what we are saying, because we don't have like this, so we have like this somewhere for some integer belonging to this set. As Tk then belongs to the down closure of x, the down closure of y, and the vertex set of P, of course, the result follows. Why does Tk belong to the down closure of x? That's because we have these inequalities, and the relation we have introduced, being a partial order, is a transitive relation. So x will be greater than Tk. So Tk by definition belongs to this set. Just like that, because of these inequalities, Tk belongs to this set, and because we are considering these T sequences to be sequences of vertices in P that are also in T, so it belongs to this. So that's why this result follows. So see, what we have proved is that our path remains any path P joining x and y, but that has intersected the tree T somewhere in this set. That's why if you remove this set, all the paths linking x and y are gone. So that's why x and y are separated. So that's why this set separates x and y. Now 2. In 2 we wrapped that up now. Let's just quickly recall what to say. S is any subset of the set of vertices in the tree, which also happens to be the same set for G, and S is down closed. Then if one now we don't need this part, so we can clean this half. So S is down closed. Now if one removes S from G, that may result in a disconnected graph. In general, we will have some components. If not disconnected, we will have a single component. But whatever the case is, the author is saying that the components of G minus S, say this is your S, and its removal results in these components. So these are the things in G minus S, the maximal connected subgraphs. Now these components are spanned by up closures like this. Spanned by, okay, not necessarily equal to the up closures, because you see the tree is there, I mean in the background it is there, that normal tree is there. Removal of S has also likely removed things from T. Yeah, in fact it has removed, because all the vertices are there in T, nothing is there outside T. So removal of S results also in the removal of some vertices of T. So the tree has been broken up into sub-trees. Okay. Sub-trees, I am saying, actually you take a part out of a tree, in general you will get a forest. The components are sub-trees. Those sub-trees may have some extra edges that give you the surviving components of the graph G after removal of S. So you will have the tree parts here that have survived after this removal of S in each component. So what we are saying, that these tree parts are equal to up closures of some vertices, remaining vertices after that removal, and those remaining vertices also have a property. They are the minimal elements, not the minimal elements, but minimal elements in T minus S. T has the T as a whole has a single minimal element, which is the root. But after you have removed these things, maybe the root has gone with S, maybe. So in general you may end up having the next smallest things, next minimal elements. If not the root, then what else is left? Among them you will get some minimals, so that below them there is nothing. So those such minimal things will have their up closures, and they will be the tree parts of these components. That's what this second part is saying. Okay. Oh, and what is the meaning of down closed? Down closed means if you take okay, so this is our S now. If you have a vertex in S, then whatever comes below S, that is the down closure of x, say x is your vertex, this is what comes, this is the root. Oh, root will be there in S. Root will be there in, let me just see the thing somewhat more closely. Okay, I said just now that the root will always be there in S. Is that the case? We don't have anything here saying that S has to be non-empty. If S is empty, okay, if S is empty, then what is the result saying? Then removal of S from G does nothing. We have G itself, and in G we have how many components? Only one component. Do you see why? Because T is a spanning tree. So if you, in the original G, if you have more than one component, how can you get a spanning tree? You can at most, you can have in general a spanning forest, no? Because if you take two vertices in different components, by the definition of a tree, they should be linked by a path. But that is not possible if you have more than one component. So because T is a spanning tree, the graph actually in this case is a connected graph. So we have only one component if S is empty, and in that component only one component, which is G itself. So this is our G minus S, or more specifically this, and in it you have a minimal vertex which is the root itself. And if you think of the up closure of the root, that has all the vertices in the tree, because everything is greater than or equal to the root. So the up closure has everything, and in fact, since everything in the tree is that is also in the graph, so the up closure of R in fact is the entire tree T, and that clearly spans G, because that's what we have here. So in this special case where S is empty, we don't have to prove anything actually. And when S is non-empty, you have something in S. Consider the down closure of that something. That down closure contains the root. So S must have the root if it is non-empty. So removal of S in the case where it is non-empty results in other minimal vertices, okay, other than the root. Okay, so now that's the entire scenario. Okay, so let us now start the proof. Since so many small things, so easy to miss, since S is down closed, the proofs are deceptively short, but a proper understanding requires many things in between. That's what I'm realizing now. The upper neighbors in T of any vertex of G minus S is again in G minus S. And clearly in the same component. We can wrap this part up, we have understood, but the second part is saying. Becoming very familiar with something through prolonged exposure, we tend to forget that when we see things for the first time, they are always like this, no matter what you are seeing in the same component. So the component, okay, let us just first copy what the author is saying and then we will try to understand. So the components C of G minus S are up closed. G minus S are up closed. As S is down closed, minimal vertices of C are also minimal in G minus S. By 1, this means that C has only one minimal vertex. X and it is equals its subclosure. No. How can it equal its subclosure? Okay, let's write it down and then we will see if it is what the author is saying. Is the statement also like this? No, it's not equal. It is spanned by this subclosure, not necessarily equal. Okay. So now comes the part of understanding these things. So what we are saying first, since S is down closed, the upper neighbors in T of any vertex of G minus S is again in G minus S and clearly in the same component. So this is our S. The upper neighbors in T of any vertex in G minus A. Okay, so what we are talking about G minus S. So this is our S, and say we have a vertex G minus S in G minus S. Say that vertex is V. It is outside S. The upper neighbors in T of this V. So this is an upper neighbor. Upper, say let us denote it by U. U is an upper neighbor of V. It's a neighbor of V. It is adjacent to V, and it is an upper neighbor because in the tree order T, it is greater than V, and it is in T. Okay, everything is in T because T is a spanning tree. There is nothing outside T in this case. This U also is in G minus S. This is G minus S. Why? Because if U is not in G minus S, it is in S. And in that case, V would also be in S because S is down closed. Anything that comes below U, below any element in S also is in S. That entire chain, do you remember? Totally ordered subset up to the root. That entire thing is in S. So that would contradict the choice of V as a vertex in G minus S. So all such upper neighbors of any vertex in G minus S are also in G minus S, and clearly in the same component, of course, because it is linked to V through a path of length 1, so it must belong to the component in which V is lying. So the components C of G minus S are up closed. Now you may have many things like this. So this is one component in G minus S. You may have another component in G minus S where you may encounter some. Encounter means if you take any vertex in this component, so this is C1, this is C2, you take the V prime, which is any vertex in C2, and you find an upper neighbor U prime that is also going to be in G minus S and in particular in C2 because it has to belong to the same component where V prime is lying. So this fact tells us that the components are up closed. Unlike S, which is down closed, these are up closed. Anything you consider, the thing above it, that is also there in the component. Okay, so the components themselves are up closed. So that's how we are getting this. As S is down closed, minimal vertices of C. So we don't need this extra component, so let us call this C. As S is down closed, minimal vertices of C are also minimal in G minus S. Now why is that so? Say this in place of these vertices, which were general vertices, you have a minimal vertex X in C. Minimal in C, not necessarily minimal in the entire graph. But if it is not minimal in G minus S, that may happen. No? We are saying that this X is minimal in C. That means X, of course, is in the tree, and in the tree order there is nothing below X in C. However, that something below X you may find in G minus S, maybe in some other component, but that does not make sense. Now, if you have something below X in this component, then these two components must be the same because of the presence of this edge. And why do we have this edge not in S? Because whatever we are saying now is we are saying those things in G minus S. So this edge is outside S. S is gone. After that we are saying that the minimal vertices in C are also minimal in the entire G minus S. So because of this we have the claim here that is true. Okay, minimal vertices of C are also minimal in G minus S. Now this implies, because of due to 1, that C has only one minimal vertex. There is no other minimal vertex. To emphasize minimality, let us consider one minimal vertex M1 here and another minimal vertex M2 here, which is different from M1. So these are two different minimal vertices in a single component. Now if you see they belong to a component, so they must be linked by a path. If you find that these two vertices are adjacent, then they will be comparable. So minimality would then imply what? Minimality of M1 would imply this: M2 is greater than or equal to M1. M2 cannot be less than M1. And minimality of M2 implies M1 cannot be less than M2, so M1 is greater than or equal to M2. Okay, and because a partial ordered relation is anti-symmetric, so these two things imply M1 equal to M2, which contradicts their distinctness. So such vertices cannot be there in C, and if they are not adjacent, have I considered the case here? If they are not adjacent, then they are joined by some sort of path in C itself, okay, because C is a component that we have after removing S. So that's why we have a path like this which has at least one inner vertex. Now that inner vertex we in fact cannot have at a higher level than these things. We have already seen, I mean, how do I justify this? We have already seen one such situation that Ti minus 1 cannot be less than Ti, and at the same time it cannot be Ti cannot be greater than Ti plus 1. This situation is just like that. Okay, why am I struggling? I can use part 1 here now. Part 1 says what? If we have two vertices x and y in the tree, then they are separated by this thing, by the intersection of their down closures. Now here we have M1 and M2, 2 points, 2 vertices in the tree, because after all the tree is a spanning tree, so everything is in the tree. So any path joining M1 and M2, and in particular any path in C that also joins M1 and M2, it should have it should be separated by this set. Now this set means what? This set in the actual tree before deleting s, okay, but you can understand that before deleting s the situation will be like this. This is that tk in where m1 intersection m2, the intersection of these down closures. Now it seems like we have drawn things like this so that the moment we come down from m1 we have left c, we are outside c. Is that the case? If that is not the case, if you continue to have vertices in C here below M1, then minimality of M1 is contradicted. So if you have found a path, and because it has to intersect, I mean those two things must intersect somewhere, that path should start like this and immediately leave C, and it will come like this, okay. That will be the situation. But what will happen then? What was the justification here? I can't seem to remember it. It's not coming to me right now. If we have two paths like this which come down like this, meet at a point and then go to the root R, what goes wrong? It has something to do with this. The nature of M1 and M2 being minimal in G minus S. Yeah, at this last stage I have got stuck. And give me just 2 minutes. Can I think of it and salvage matters? This type of path is not allowed in G. Why? What am I missing in my argument? Oh, yes. You see, even after removing S, we have got a component C, which by definition is connected. So M1 and M2 are linked by a path. But if every such path must pass through this, and the way we have things here, we see that this vertex, this tk, which where things meet, this tk should belong to that path, say this path, and that tk belongs to S. Why? because I have just now said that we have to immediately leave because of the minimality of m1 and m2. The moment we start traversing such a path, we have to immediately leave. So this tk that we have got must lie in S. But if that is the thing, then removal of S will sever this link. So how are M1 and M2 linked in C? So distinctness of M1 and M2 would create this impossible situation. So that's why M1 and M2 cannot be distinct. This means that C has only one minimal vertex and it equals its up closure. No. C does not equal, this I was right in guessing that this is wrong. Does not equal, it is spanned by so that means we won't have M2 here, we will have only M1 because M1 is the minimal and we have already seen that the components are up closed. So the up closure of M1 is the tree part in C. Okay. And that's just it. Have I missed something here? Because it is a component, everything must be linked to everything else by a path, right? So can we have a situation in which we have two such tree parts which are linked by something that is not in the tree, by an edge, of course, that is not in the tree? No, because if we have such things, I mean, we have one tree part here, another such tree part, say, in the same component, but the linkage between them is through an edge that is not in T. Can that happen? That should not happen, because otherwise this alone is unable to span C. That cannot happen, but why? Will that result in two different minimal elements? Every tree part will have a minimal element. Yes. So that's why this cannot, or you can argue slightly differently also. It is spanned by the up closure of X, that is this. Okay, so that completes the proof. So these are two facts about a normal tree in a graph, that any two vertices in the tree are separated by the intersection of their Dunn closures, and if the tree is a spanning tree in the graph, then its removal results in some components. Sorry, what am I saying? Not the removal of the tree. If we have a spanning tree in a graph and we have a set of vertices in the graph, which is down closed, then its removal results in some components, at least one component of course, which is each component is spanned by up closures like this, where these are minimal elements in T minus S. Okay, so the absolute minimum is gone, the remaining lowest possible things will then generate other parts, span the other parts. Now I will have to end the video here, but let us see quickly what comes afterwards. There is one result that is left. Normals, after this the author says, normal spanning trees are also called depth first search trees because of the way they arise in computer searches on graphs. Depth first search is a way of searching things in if a computer uses an algorithm that is depth first search, then it first considers the root and then it goes to the higher levels branch wise. We will see in exercise 19, when we start solving the exercises of this first elementary chapter, preliminary chapter, we will see in exercise 19 what depth first search is. This fact is often used to prove their existence, that is, existence of normal trees. And the next proposition in fact makes normal trees really, it says that you can find normal trees everywhere. It says that if you have a connected graph, then in a connected graph you can always find a normal spanning tree with any chosen vertex as the root. So that we are going to state and prove. State means we have already stated, this is the statement. We are going to prove it in the next graph theory video. And after this we have a group theory video also. So that will be all in graph theory for tonight. If you want to say something on this, you can write in the comment section below. So that's just it. So see you in the group theory video.